Okay, so this is the last part of this lesson. So in this I am going to show you one more linearization strategy for the convective term and see how this helps the convergence problems that we were facing. Okay, so basically, so this linearization is actually a truncated version of Newton option in the sense that we ignore the higher order terms in the Newton option. Higher order in the sense of delta U, the increment. Okay. I'm not going into the details, so I'm going to show you the final term. Okay. So this is the approximation that we use for the convection term. So instead of the fully nonlinear one, we use this linearized one. So here we have three terms, not one, we have three terms. So the first one we have already seen in the type 2 stream. The third one we have already seen in the type 1 stream. Okay. And in this type 4 stream, so we have the extra term here. So this expression comes from the Newton option stream when so when we linearize. So here we are only keeping the linear part of it. We are ignoring the nonlinear part. Okay. So this is linear. We don't need any iteration iterations to solve at each load step. And this is an implicit stream. And this stream it covers even quadratic convergence in time when we use quadratic streams for acceleration terms. Okay. If you want more details, you can refer to this my paper. Okay. So where I study extensively, comprehensively the convergence behavior using some benchmark examples. Okay. Coming to the weak form. Okay. Again, it is very similar. So here, this is our linearized expression for the convection term. Okay. And we have the same in the stabilization part. Here we have three terms and one of them is a known value. Okay. So un dot del un. So this is a known quantity because we know un. So we can move it to the right hand side. So that means we get one extra term in fu and fp. Okay. So because of this we get one extra term in fp. And on the left hand side we have two terms in un plus 1. Un plus 1 is unknown. So we get two terms to the stiffness matrix. So eventually once we discretize, okay, I will show the terms. So to discretize, we have already discretized the first term for type 1 for type 2 stream. Now we discretize the second term. Okay, to discretize, first I expand it in terms of the components. And then I write the final expression as a product of matrices and vectors. Okay, so first we segregate all the terms for the known quantities, which is un. So here we have the derivatives, and then we segregate all the quantities for the unknowns. So this is how we, like I said, it comes with experience. So but if you like follow this like this, so segregate all the terms for the known quantities into the matrix first, and then segregate all terms into the unknown quantities into a matrix or vector. Okay, that follows the first matrix. So we are expressing this as a product of matrix, product of two matrices or product of matrix and vector. Okay, so once we segregate, we get these expressions. So this is actually our gradient tensor. Okay, in 2D del un, and this is our velocity vector unknown un plus 1. So this is a known quantity. We can evaluate it at every draw point, and we discretize u. Okay, so we discretize un plus 1 as nuu. Okay, and similar to what we did before. Okay, so for the test function and also after separating w transpose and u, so the term inside the bracket is the stiffness contribution to ku, rho nu transpose del un nu. So here note we don't write del un as a matrix as a 4x1 because here we want to preserve the dimensions. We need to keep it as this. So for example, so this is 2 by 2 and NU is 2 by M2, M like 2 by 2M. So if you change this to 4, then there is a mismatch in dimensions, right? So that is why this quantity we keep as it is, as a 2 by 2 matrix. And similarly, we can discretize the term in the stabilization. Okay, the stabilization here. So in the final form, so we have this 2 by 2 Blot matrix system with one extra term to FU and FP and two extra terms to KU and KPU. This term we already know from our type 2 linearization. This is the only extra term, and this term we already know from type 1, except that here we have plus, whereas in type 1 we have minus. So be very careful with the signs. So we can implement this again. So to implement this, we need to calculate gradient of velocity, so which we already did. Okay, so we calculated the gradient of velocity from the previous velocity. Okay, so that is already a 2 by 2 matrix. Okay, 2 by 2 matrix. So we don't need to create any another additional variable. So for type 4 stream, on top of the contributions for the Stokes flow, we have these contributions, okay, for Navier-Stokes. These are the extra terms, as you can see. Okay, for FU and FP we have plus here, and this is rho UN DUN. Okay, rho UN DUN, and for FP the same, but in terms of the stabilization parameter and GP transpose. Okay, this is the first term for KUU. First term for KUU. Okay, so this is from type 2 type 2 linearization, which we already covered, and the same for KPU. And the second term is this rho NU transpose del UN NU. Okay, so NU transpose rho del UN is gradient velocity, NU divided. Okay, similarly for KPU. Okay, so as you can see, once we successfully write the stiffness matrix function for Stokes flow, it is very easy to extend it to Navier-Stokes. Now I am going back to the main function. We don't need to change anything in the main function. First I run it for a time step of for a Reynolds number of 100, and the other things the same, remain the same. So maximum time step load steps of 100, time step of 0.1. Okay, run it. Okay, so there is no divergence here. Now if you look at the convergence of error norm, okay, as you can see, we are increasing the load factor, okay, by time step size. So 0.7, 0.8, 0.91. Okay, at load step of 10, we reach the maximum load factor of 1, and after load step of 10, we keep the load factor the same. Now, okay, so we don't expect convergence until 10, but after 10, okay, so now this is the error norm at load step 11, and this is the error norm at load step 12. As you can already see, the error norm has reduced substantially, like almost by 3 orders of magnitude. So from -2 to -5, like 10 power -2 to 10 power -5. And at the load step 13th, the error norm now is 10 power -11. So within 4 load steps, the error norm has reduced by a factor of 10. Sorry, not a factor, by an order of 10. So with only a small modification, we could achieve a substantial improvement in the convergence of load steps. Okay, so this is how we have to think. Okay, so we can simply reduce the load step size, time step size, and increase the number of load steps and run it with the type 1, type 2, type 3 streams. That would work. That is what people typically do. And we say, okay, we use high performance computing, we use GPUs, it's faster. But that's not the type of thinking that we want to see in the computational community. We want to be able to develop streams that substantially reduce the computational cost without having to use high performance computing. Of course, we do need high performance computing for solving large scale problems, but these minute changes can take as a long way in solving large scale problems. Okay, imagine using this method and high performance computing and the type of problem that we can solve. Now let us see if it remains the same for a higher Reynolds number of 1000. Okay, we don't see any divergence. Velocity is smooth. Okay, we have reached the low step of 10. Okay, so now it has, again we see this almost the same type of convergence behavior within 4 load steps. The error norm are reduced by here by a factor of like by an order of 9. Okay, from 10 power minus 1 to 10 power minus 10. Again, this is a substantial improvement. Instead of using 1000 or maybe 10,000 load steps, we can solve this within like 13 load steps. Okay, so you can you can look at my code. Okay, I will share this. You can also go through the slides, understand the method, and once you understand it, you can solve, like you can set up and solve other problems like flow past a cylinder or flow past an aerofoil. Take an ATRA 0012 or some any other aerofoil, get the mesh, set it up in Gmesh, get the mesh, solve it for an answer number 10,000. You can easily solve it for an answer number 10,000 with this method. At least 1000, so without any issues. If you want to solve for higher Reynolds numbers, flows, then we can add additional stabilization, that what we call as streamlined upwind petrorelactin, which is what we have used for getting rid of spurious oscillations in the convection dominated flows. So we use the same here for stabilizing high Reynolds number flows. Okay, so this is applicable to either like equal order elements, that is we can use with PSPG, or we can also use the SUPG with the influx of stable elements for high Reynolds number flows. Okay, and like if you are also interested, so you can refer to my GitHub repository, so where I have this formulation implemented and parallelized. Okay, so parallelize up for like parallelize for distributed memory computing using OpenMPI and PETC. So I managed to solve like a problem of up to 1.4 million cells. That's about, if I remember correctly, 6 million degrees of freedom. Okay, and we should solve more. Okay, and this is the advantage of like using better methods. Equal order interpolation, ease of implementation, better linearized versions, no iterative streams, better linearized versions, reduce number of load steps. So by solving problems separately one by one, we try to solve bigger problems efficiently. Okay. Any questions, please post in the comment sections, or you can also email me if you have any issues. Okay. Have a nice Christmas. Bye bye.